Okay. Gaurav, the screen share is visible?
Yeah.
Okay. All right. So this is the main window of this software called, now it's called AWR Design Environment. It's used to be called Microwave Office. So I will probably use these two words interchangeably. And as I mentioned last time, it's very easy to use and intuitive to use as well. And it allows you to check many of these concepts in a very simple way. So I'm going to be using this extensively to teach. And also a lot of your assignments and even exam at the end will consist of using this software to solve various problems. So that's why I want to spend some time teaching you how to use this. Of course, we will do that more as we go along as well, because as of now, most of you don't, at least I'm guessing, don't have any background in thinking about microwave circuits and networks. So many of the items here will not make much sense. But I will try to point out those things. And some of them are fairly straightforward, so I can introduce them quickly here, even before we do a formal introduction later on. So let's just look at the left side here. So this is called the project window. So if you look at the bottom, there are these three tabs. Mostly we'll be using these first two, the project window tab and the element tabs. So I'll come to the element one a little bit later. And here there are several further tabs here inside the project thing. And I'll just quickly go through them. Design notes is nothing. You can just type something about here. In the past, I've used this location as a way for people to submit their homework assignments by typing out the answers here. That's one possibility. Project options is related to various parameters about the particular project you're working on. I will come to the details later. Global definitions I will skip for now, but basically there are some ideas of global and local variables here. So there is some amount of programming and scripting that can also be done in this, which allows you to do certain kinds of set up a certain sequence of measurements or make certain common variables used across different of your microwave networks and circuits. So you can define some global things out here. Data files I will ignore for now. System diagrams I've actually never used. It's not something which is very common. The most common one we're going to be using is this thing called circuit schematics. Okay, so you just right click it and you say new schematic, and you can give it whatever name you want. And it opens up this. This is basically your drawing board. This is where you will build your microwave circuits. Okay, so if you want, you can think of this as a breadboard as well. And you can have many schematics in the same project file. As I said, if you want to create interdependent things, sometimes multiple schematics are, apart from just having several different things, you can also create things like submodules in programming, where you can draw some microwave circuit here, which can be used, the whole thing can be used as a building block in a different schematic. So that can be useful for more complicated networks. So it allows you to do that. And I'm just going to mention whatever comes to my mind today, just as an introduction. And then when we will encounter them again, as the classes go along, I will explain them in more detail. Netlists, again, I'm going to ignore for now. It's not something we'll use that frequently, or maybe probably not at all in this course. The next one we will use a little bit later in the class is called an EM structure. So as I was telling you in the previous lecture, that you can make circuits. So circuits here means that every object is predefined. You just drop them here, and we will see that in just a second. But you can also create the physical structure of a microwave circuit. And that's done here. So again, you right click and you can say new EM structure. There are many more options here related to what kind of solver or simulator we are going to use. And there are several options, but we'll be using this first one for all of our work. So you just do that and you again get a drawing board similar to this, but this is a different type of a drawing board. Here you cannot drag and drop the elements which are here, which are used for the circuit. Here you actually draw physical structures. And as I was mentioning, you can draw them in a CAD software outside and import them. I think there's a way to do that here. If I right click, let's see. Okay, maybe it's not here. I will come to that when we actually look at EM structures. And there are some other things like enclosure, which talks about the boundary conditions of your structure. And we will look at that in more detail later on. Output equations are something that can be used for doing some analysis in an interesting way. I will talk about that after I discuss graphs, because this is the second most common thing we'll be using, is to create results of the measurements you're doing on these structures you have created. So graph is how you do it. And again, you go here and you say new graph. And there are several options. Some of you who have some familiarity with microwave measurements on instruments might recognize some of these things, but we will mostly be using rectangular plots, which are just standard XY plots. There's also something called a Smith chart, which used to be a common way of visualizing microwave measurements in the past. Nowadays, it's not used so much. It's basically excuse me. It's a sneeze coming, which I'm not able to get out. It's basically a polar plot, and it allowed you intuition about various things, that in that polar plot, if something is happening or certain point is there, how do you interpret that? These were all tools which were very useful before the use of computers extensively for doing these kind of analysis, because now everything can be just calculated by the computer. You don't have to do anything. So these were rules of thumb. And in fact, if some of you have started browsing through POSAR, you will see that Smith chart is something which is given a lot of importance. And there were standard tools and tricks to, how to read a Smith chart and understand various things about a particular network. But we will mostly use rectangular, and sometimes I'll show you what a Smith chart actually does. So you just create that, and it creates sort of a standard template for a graph. Again, you can rename all of these things out here, and I suggest that you use the names appropriately when you submit homeworks and things like that. It will be a lot easier to go through. So give them appropriate names as you go along. It's just a question of making a habit to do it, and then it's good to go. Once the graph is defined, this is just a container, then the main thing you have to define is something called a measurement. So you right click on that and you say add measurement. And here there is a whole range of options. We will not even be covering a fraction of them. But the most common measurement which we do is the one which comes by default highlighted. And this is called scattering coefficients or scattering parameters or S parameters. And this is basically, as I was telling you last time also, it's similar to the scattering things you study in quantum mechanics or even in electromagnetic radiation, if some of you have done it. And essentially it tells you when a wave is incident on some structure, what is the ratio of ingoing to outgoing waves, what is the ratio of transmitted versus reflected waves or incident waves. So these all create various kinds of scattering parameters. It's usually defined in a matrix form. Here, of course, you refer to them with these indices. Often the scattering parameters come with two indices if it's a two-port network, and it's actually it always comes with two indices. Sorry, the network only changes what numbers the ports take, and then there is an index for the two-port, which is the first one here, 1, and from port. So this is a slightly odd thing to get used to, because we might always usually write from and then to, but here you write the to. So this is the target port, which means where the signal is received, and the from port is where the signal is sent from. Okay, so these things will become clear when I give specific examples. So S11, which is what it is set up for right now, means both the incident and the reflected, or the collection port and the source port, are the same. So this actually is what is also called a reflection measurement, because you're sending signal from the same port and then looking at what is coming back, and this plots the ratio of the voltages for the signals. Again, why voltages, why not power? These are all details which we will look at as we go along in the class. And this number by default is a complex number because there is amplitude and phase information involved. And the bottom here allows you to choose the complex modifier, because this is a regular graph. The x-axis is mostly always frequency, because we are always looking at these as a function of frequencies so that we understand how the response changes as a function of frequency. So you cannot plot both real and imaginary on one axis. So you can choose real, imaginary, magnitude, angle, and there's something called angle U, which U stands for unwrapped, and we will discuss that later. It's basically whether the phase is restricted in the plus minus 180 degree, just sort of one full circle, or you allow it to run completely to other values as well. Because your changes in phase can still accumulate to be larger than 360 degrees in a given circuit. So that can be sometimes useful for visualization. And we will discuss these things in more detail later on. And then you can also choose whether the data is plotted in log units or not. So dB stands for decibels. And usually the magnitude is plotted in decibels. Instead of looking at the linear magnitude, you look at the power in dB. So that gives you basically a ratio of power and in log units. So these definitions of those we will also look at later. And that's it. Then you click OK. And here you can choose which source. Data source means which schematic or which EM structure. You can even say all sources, so it will plot the same quantity across many different schematics, which we rarely use. So right now, because nothing is defined, it's not giving us any value here. So we will do this example in just a second after we have gone through. Okay, so this then defines quantity here, and then it will plot that quantity once you run it. So there is this little lightning indicator here. It says analyze. So when you press it, it will run the simulator. So right now there's nothing, and it's saying something failed because the EM structure here is sort of empty. So I'm going to delete this because we are not going to be doing EM structures today. So once you run that, it'll plot the results here. The question now is, of course, what frequency ranges that you can specify here in project options, or going to here, options, project options. And there are many other things which we rarely use. So for example, there's one for global units, and you can basically decide what are the standard units for dimensions, for inductance and capacitance. We will mostly not mess with it. So the thing we mostly change is the range of frequencies. Okay. Again, it's a silly thing to go into detail, but this is a place where mistakes often happen because of a peculiarity of how this is done. So currently it's saying the current range is 1 and 2 gigahertz. So this window here gives you the list of frequencies on which the simulation is going to be carried out. Okay. So each simulation is an independent simulation for that particular frequency. And how do you create a range here? You use this little tool here. So you give a start frequency. So let's say we say 4 to 8, and the units are given. So these are all in gigahertz. And by default, it has this radio button, which is replace. Okay, so replace means that whatever you do here will replace whatever the original list has. But you have the option of adding to it or subtracting from it in case you made a mistake or you change your mind and you want to change it and you don't want to do the whole thing again. I mean, okay, it's a very specific things, sometimes useful. Most of the time, it creates problem. And the biggest mistake, which at least I remember many I have done and many of the people have shown done, is that after you do this, you have to click apply before you hit OK. Unless that numbers comes here, it will not simulate. And this can be something which you miss out. So let's say 4 to 8 gigahertz and 0.1 gigahertz step size. Then you hit apply. So then this list gets populated from 4 all the way to 8 at 0.1 gigahertz spacing, and gives you total number of points here, right? So if I want to show you the thing about addition, so I can now go from say 8.1 to 9, but I now say add and I hit apply. So the list is maintained and it will add points from 8 to here. Okay, so this of course is sort of silly, but where it can be useful is when you don't want the same resolution in the frequency spacing for different ranges of frequencies. So maybe there is a particular range of frequencies, say between 6.4 and 6.5, where you expect some feature to come because of your previous analysis of the circuit. And you can do over there something which is finer. So let's say I go from 6.401 to 6.499. And here I want to do it at 1 megahertz spacing. So here, obviously, I want to do add because this is now an asymmetrically spaced list. And I can hit apply. And then you see that the total number of points is these. And you can see the points here. Okay. So you added about another 100 points in then, and then it comes up. So this can sometimes be very useful if you have two scales over which you're observing something, that there's an overall broad scale of large range of frequencies, and then you want to narrow some very sharp feature. Typically we are going to be looking at some kind of a resonance or some poles, and you would want to zoom in, but you don't want to solve at the same high resolution everywhere because it'll take time and it's not needed. Okay, so that's how it's useful. Same way, if you want to you made a mistake and you just want to delete it. So if I just now use the same setting and go to delete and I hit apply, then those new points we just added are removed between 6.4 and 6.5. Okay, so that's really the use thing. You can also add a single point just with one value here. And again, all of these three options are available. Okay, so this I'm just sort of going over in detail. It's kind of a silly thing, but often mistakes are made here. And one other very important point here is that, so this anyway is now done, so I can go back. Is remember we went here, options, project options, and we defined the frequency. This now applies to any circuit you have made in this project file. So whether it's a circuit schematic or an EM structure, this is the global project option definition. The same thing can be, you can go from here as well. It comes to the same window. Okay, but it is possible to specify a different range of frequencies for a particular circuit. So for example, if I go here and I go to this options, in the frequencies tab, by default, you will have this tick marked which says use project defaults, right? So this is again giving you the list from what we had defined, but you can change this, you can remove this, and here you can define a completely different frequency range. Then this particular circuit will be solved with that specific range. So this can again sometimes be useful when you're creating a more complicated circuit with many different parts and things like that. Okay, so again, as a matter of the content we're going to be covering here, we'll probably rarely use this feature, but it's sort of good to tell you in case you get confused by seeing this option show up. So most commonly, we'll always use project defaults. This particular aspect, when it comes to EM structures, is actually the opposite, if I remember correctly. The default option is, I think, not to use the project defaults. And there is a good reason for it. And I had mentioned this last time, that EM structure simulations are finite element simulations which solve Maxwell's equations of, breaking up the whole structure into small pieces. And they're much, much slower, orders of magnitude slower than a circuit simulation. So you probably don't want to solve with as fine a resolution in order to save time. So that's why it always has a different thing, but you can also force it to use the project defaults as well. Okay, so this is something to remember, so that sometimes I've seen this problem happen, especially when I taught this course last few times, is that you run something, but the simulation is actually carrying out on a different set of frequencies because these things were not set up properly. Okay, so let me delete that again. Okay. Now let's go through the rest of the things. I think most of these things are now not really useful. The output files are created when you run these simulations, so it shows some things will start showing up here. Nothing to really worry about. Okay, so that's basically about this thing. The last thing I wanted to stay here was, if I go back to this output equation thing, here again you can create one output equation tab. This allows you to define the measurements, which is basically some quantity as a function of frequency, as a variable, so that you can carry out operations on those variables. And that can be useful sometimes, that if you're actually taking the result of a measurement and doing some calculations on top of that. And that's where this gets used. And the way you do it is you come to the output equation. Again, you can have many output equation tables here or these windows. You can set up their own names. And then you come here and it's sort of a strange command. You go to draw and you say add output equation. Okay. So you see this window now here looks very similar to the measurement window you had seen in the graph part. Right? So now you define a variable. So let's call it my measurement. Again, you can define these port parameters. Here you have to define the schematic on which the circuit is being made. So maybe just to show this properly, better to have a schematic here. So I'm going to quickly draw something. I'm just doing this quickly now, but we'll come back to this on exactly what I'm doing in just a few minutes. Basically, I've just created a one-port network, just a capacitor connected to a port. Okay, so don't worry about this. I just wanted this so that I can show it here. So go back to output equations, draw, add output equation, my measurement. So now you see in the data source, it gives me an option. Here you cannot do that all sources. In fact, it will not even show up as an option. And since it's only one port, there's only one measurement in the scattering parameters you can do, which is S11. Okay. And again, you can choose the modifiers, but usually these calculations are often done in complex domains. So you can actually keep it as a complex number. So, and you have to remember that. And then it just shows up like this. And this is an example of the kind of scripting one can do, because I can write now further equations below it using this x equal to y icon here, or using this draw add equation thing here. And I can call this this my measurement variable in this equation. I can do things to it. So for example, I can write something like, I've forgotten whether I'm writing the exponential function correctly, but I can basically write a complex number here. This might be wrong, but I'm just giving you an example of what. So one of the things you might want to do, because it's a complex number, you can rotate the reference frame, and that for that you have to multiply by some exponential, or you might want to calculate something else from these quantities, which is not as a standard list. So you can do that. And the nice thing is that these output equations then became available in your graph as a way to plot them. So instead of just plotting the regular measurement, you turn that into a variable. You calculated a new variable, which is a modified version of this thing, but you might want to see it. So you can, when you go to this graph here, and you say add measurement, now in this, you can go to data. Sorry, maybe no, output equations here. So that's one type of measurement you can plot. And then you can choose the document name, which is output equation, and the equation name. And it says you can mod measurement, right? And again, you can give the modifiers here, and then that shows up here. So this can be very useful if you're doing some sophisticated analysis on your simulations, and you can write scripts. And I'll go into the details of the scripting later on, but basically it's an odd thing because, there's no order here, but it sort of goes from left to right and top to bottom. What that means is that I cannot have this written on top of that. That won't work. It'll throw up an error because it doesn't know my measurement till it comes down here. So this is not the most sophisticated scripting environment, but you have to be careful about this when you do that, because you can also have these kind of equations in your schematics as well to define common quantities which are being used again and again. So let's say there are 5 capacitors in your circuit. All of them have the same value, but you might want to change them together. So instead of specifying, say, 1 picofarad on 5 capacitors, you define a variable called C, call it 1 picofarad, and then just enter that variable into the values of the capacitances. Okay, so that's useful. And again, if you're doing calculations with those, and if you're computing these values on the fly, then it's important to remember that the ordering has to be sort of top to bottom and left to right. That's how it sequences. So this, if it's roughly on the same level on the right-hand side, is okay, but this is not, and not is this. Okay, so yeah, so that was about these project things. I can maybe pause here a little bit if there were any sort of basic doubts at this stage. We are just going through some very trivial things right now, just familiarization, but are there any questions? Okay, I don't know if yeah, okay. And always use the hand thing so that because we are quite a few people, we might have problems if we start speaking over each other. Okay, give me 1 minute. Just want to drink some water. Okay, so now we will make one simple circuit to give you an example. I'm going to delete this in case this throws up some error, because I'm not sure if I defined this correctly. And I'll delete this measurement as well. So let's go back to schematic. Okay, I seem to have made a typo here. Okay, so I have some objects already here. One particular circuit which we are going to use very frequently for lots of things is a simple LC oscillator. Okay, so I already have a C there. So let me bring another component. So now we can look at this particular element window more carefully. So this is circuit elements. You can ignore these other 2 things for now. And in there's again a huge number of things. We will only be using a subset of these as part of this course. The most common ones we use are these so-called lumped elements. Okay, so maybe this is a good chance for me to say something about lumped elements as well, because this is one aspect which of circuits which we are familiar with, and this is actually the main point which distinguishes conventional electronics versus microwave frequency electronics. Okay, and that is the absence in microwave domain of ideal lumped element circuits or devices. Okay, so lumped element basically means, and the other term is, which is opposite to this, is called a distributed element. So something which is extended in space, distributed in space, versus something which is like a point object. So even though we know that we have seen capacitors and inductors and they're not point objects, the reason they are called like that is that it depends on their size relative to the wavelength of electromagnetic radiation or at the frequency you are operating on. So in that context, they are almost point-like. And if that is true, they're called lumped elements. Of course, in reality, in any situation, there is never a perfectly ideal lumped element. So all of these are approximations. But all the circuit analysis in electronics you have learned so far is under this lumped element approximation, that there is no difference in the phase of signals across different points of an extended circuit, because all of them are very small compared to the wavelength. That automatically satisfies for the typical frequencies we usually work, which is like maybe a few kilohertz to megahertz, maybe at the most, where the wavelengths are huge. They are meters and like kilometers long at the speed of light. If you take in the speed of light and calculate it for the relevant frequency. So that works out. And unless we use specific types of elements which have the wave aspect of microwaves inbuilt into this, that is the regime under which these calculations are also done. And for some circuits, we do use lumped elements. They do exist in the sense that you can buy a capacitor which is supposed to work at the microwave frequency range. It's just that they are not ideal. Okay, but everything we do here in this circuit domain gives you the ideal response. And that's often the starting point of designing any microwave circuit, is that you look at the idealized response and then you worry about the fact that it's not really, and in most cases, it won't matter. Okay, so these lumped elements will always come with terminals. So these are these little crosses here. So there's a cross here. These are the connection points. And essentially, we're going to be worried about, or this, the way the system calculates, is that there is basically some voltage difference between these two terminals. Let me just delete this as well, between these two terminals. And there is no difference between this point and this point below it. These are all at the same potential, right? The only potential difference comes across is between this plate and that plate. And similarly, there is no difference here. So that's, again, emphasizing this aspect about the lumped element. Okay. So I'm going to now create a simple circuit. So I have taken a capacitor. So this was from here. So when I, under lumped element, I click capacitors. And under that, there's a whole bunch of things here. I will not go into this detail today, but you choose this one for the simplest case, which is this cap, which says capacitor closed form. There are other kinds of things. If you look at cap Q, and I will discuss where those things are used later on. They are basically small amount of non-idealities introduced into the model itself of the thing. So that allows you to be a little bit more realistic when you're using, let's say, a particular brand of a capacitor. There are ways, I haven't used it in a long time, but you can actually import the data from some commercial model. By looking at the model number, you can import that data here and it will simulate it according to that. So that can be useful to really know that, okay, you have created an ideal circuit. Now you're actually making it using components you have purchased from somewhere, but you can now test what would be the real performance you would expect, given that that capacitor you purchased is not really a capacitor, or it doesn't behave like a capacitor over all ranges of frequencies, and it has some other, some resistance, some conductance, and so on and so forth. Okay. So for the most of the cases, we'll use this first one here, cap. So now I want an inductor. So the inductor is here. And again, this has even more options, but the one you want to use is the simplest one, which is down here. Unfortunately, it's not the first one in the list for some reason. I think it's alphabetically sorted. And here, IND, inductor closed form. So you just drag it from there and it comes here. And while you have not clicked anywhere, you can right click and cause it to rotate like this so that you bring it in the right orientation. So then you drop it and then you can connect this. So remember this icon changes to this wire whenever you go onto the terminal. And you have to click there. You cannot click in other random places. Okay. So that completes this circuit. Now you bring this and connect the ground. So there has to be always a ground terminal. So this ground object, I got it from here at the top. Okay, so you can bring it from here like that. And this is something you have to always remember, that there's always going to be a ground reference. And then the last thing is this thing called port, which again is here. So let me delete this and bring that again. Okay. And the port is basically your reference point from where a signal is generated and also where a signal is detected. Okay. So it's a odd thing. So it's sort of a source and a detector at the same time from the perspective of what you can do when you draw these things. And you can have many ports in a circuit and the system automatically numbers them. So the first one was 1, the second one is 2. You can of course change this. You can call this 2, but if you put 2 of them the same, then it'll throw up an error message at a later stage. Okay. And there's a very important thing it says here, Z equal to 50 ohms. So this represents the impedance of this port. Okay, and this is one of the concepts we'll be discussing in a lot of detail in the first couple of lectures. But this, in a simplest sense, means that if I think of this as the detector, so by detector, I mean the circuit which is looking at, so when I connect this over here, it's going to measure some property of this circuit by analyzing it here. So, it's like, in some simple sense, you're saying you have connected a multimeter, some kind of a probe at this particular point. And in this detector, if you think of this as a detector, even though I said it's both a source and the detector, this 50 ohm number implies that this point is connected to ground with a 50 ohm resistor. That's what this means. And a 50 ohm resistor, not a 50 ohm impedance, right? So I'm sure you're familiar with the idea that there is resistance and reactance. So things like inductors and capacitors have reactances, but a resistor has resistance, and an impedance is a combination of both. So resistance are real, reactances are imaginary. So you have a complex impedance. So it's very important to remember that this 50 ohms refers to a real 50 ohm resistance. In terms of how this circuit will respond, so for example, if I put a charge on this capacitor, now I'm sort of using this example because this is something you might have done in your electronics and other courses before, that you at time t equal to 0, you put some charge on the capacitor and then you look at how that charge changes, right? Now, if I put a charge here at time t equal to 0 and look at how the system evolves, the way I have to think of this circuit is an inductor, a capacitor, and a resistor of 50 ohms to ground. The port, even though it doesn't have a ground reference here, it's sort of assumed. So I'm going to annotate on the same screen using my other Zoom connection here. Let me see if that works. I can never figure this out. What is this? Yeah, sorry. Great. Now it's working. So what I mean by this is that this can be replaced by a circuit which is like this. This port here, in the sense of a detector, is equivalent to just a resistor which has a value of R equal to 50 ohms. Okay, but I also said that it's also a source. So a more realistic representation is something like this. I'm going to draw a voltage source V and a resistor which is now connected to ground, and this box here, oops, sorry. This is what this means. Okay, so remember, again, I know that I have not asked you specifically, but from previous experience, I know that electronics is unfortunately taught very poorly in most undergraduate courses. I don't know whether you have already taken some courses in TIFR, maybe you should have. And again, it's not a subject which is liked by a lot of students. So I don't know whether you remember this concept, but an ideal voltage source has zero internal impedance, which means that this part of the circuit doesn't have any resistance. So the previous model with only the resistor is still valid. So from the point of view of the circuit, it looks like a 50 ohm resistor. So this is 50 ohms connected to ground. Okay. And if you have a voltage which is finite, then of course that rides on top of that. And again, this can also be drawn in a current source model. And I think some of you are getting nightmares about the Thevenin and Norton equivalence, but you could also draw it as a current source with the value I, which is equal to V over 50, because the previous one was 50 ohms, and this is 50 ohms. Okay, and this box is the same as this one. So that's what putting a port here really means. Either of these two are equivalent, and which means I can excite. And the way you have to think about the detection part, remember that this particular point and this particular point are, if there is no voltage, they're actually have no resistance between them. So the return signal, or if you're measuring something about the circuit, that's the sort of the voltage dropped across this 50 ohm resistor. So you have to assume that there is some other measurement element which is connected across that 50 ohm, and it's some idealized voltmeter. So remember, an ideal voltmeter has infinite impedance, so it can measure the voltage drop across that resistor, and that's how you detect. So I'm going into this detail, but this is completely not needed to for you to know what is going on in this circuit. It will do all of these things by itself. But this is what it means in even real life when you connect to a port. Now, where do these ports exist in real lab environments? Your microwave generator will have a port. That's where the signal comes from. How do you model that microwave generator? Like the way shown here. It's an ideal voltage source with a 50 ohm source impedance. Okay, or it's an ideal current source with a 50 ohm source impedance in parallel. Okay, so that's why you can see that these both circuits effectively give you a 50 ohm to ground with respect to this point. So it's like as if a resistor was connected to this. that's how this circuit will behave. So you can see another important aspect, and I will be coming to this particular point over and over again throughout the course of this lecture, because this is something which is non-intuitive for people who have worked only with low frequency circuits, that connecting a microwave port or a microwave measurement device to a circuit is always introduces this 50 ohm to ground. This is not true for low frequency circuits, right? What is the equivalent of that? That you connected a multimeter across a device, and you ideally in those circumstances don't want the multimeter to change anything about your circuit, right? You don't want to introduce any impedance across it. So that's why an ideal voltmeter has infinite impedance. Of course, in reality, again, no voltmeter is that ideal that it has infinite impedances, but it's high enough in the context of the circuit that it doesn't matter. The errors are very small. This is impossible to do in microwave, or nearly impossible in most circumstances. And this is one of the points we'll be discussing later. And this 50 ohm, why it is 50 ohm is again a convention, which I will explain in one of the upcoming classes. This is sort of the convention which is used, that everything has this particular characteristic impedance and a source impedance. So right now we have only talked about source impedances. We will talk about the characteristic of the characteristic impedance in just a little bit. That's be the last thing I'll cover today. And these all have to be the same because we are really talking about waves now, and these represent the condition where waves can propagate without having any reflections in various scenarios. Of course, if you intentionally define something which has where you want a reflection, you will have it. But this ensures that when signal is propagating from a source onto a transmission line, which is what we will discuss next, onto a receiver, that along this kind of a situation, you don't have reflections, or you have the smallest amount of reflections possible. So, in the context of optics, this is like putting an anti-reflection coating to make the impedances match so that the reflections are canceled out. This is important because in most of the simplest cases of microwave circuits, you have some source and you want to deliver some power to some load, which is connected via some cable, which is your transmission line. And you don't want the signal to be getting lost in any of this process. So this has to be matched. So again, to summarize, all microwave sources have a 50 ohm source impedance. Again, to contrast, in low frequency circuits, we call an ideal voltage source as something which has zero source resistance, because that's usually considered bad, because any source resistance means that you will lose some power in that particular resistance and you will not get the entire voltage dropping on the load. In microwave frequencies, that is impossible to do. So you always choose a situation where the source impedance is also 50 ohms and the load is also 50 ohms, right? So what that means is, now let me draw another circuit here. If you had a low frequency situation where you had a voltmeter, a voltage source, and you were driving some resistance R, right? If you want this voltage to appear entirely across this resistor, which is what your goal is, then you would not like any other resistances to be present here. Now, this resistance could be the source resistance of this circuit. If that happens, you will not get the entire voltage dropping here. You will not get the entire power dropping here. And that's what you would like in the ideal low frequency case. In reality, you would like the same thing to happen even at high frequencies. But as I said, it's not possible. So the next best thing you do is, instead of having RS equal to 0, you have RS equal to 50 ohms. And you also have R equal to 50 ohms. And now this circuit should be familiar to you. It's a voltage divider with equal load and source resistances. And this has a property. Does anyone remember what property this has when you have equal resistances in these two locations?
Maximum power transfer.
Exactly. This allows for maximum power transfer from one to the other. And that is what you want in a microwave circuit. And in most cases, this this eraser is very funny. You will actually have a more realistic situation is your source is going to be in one location. So this is my source box. Your load is going to be in another location. This is my load. So remember again, this is 50. This is 50 ohms. And here you connect a cable, which is your transmission line. This cable also needs to have a very specific property in order to ensure that the power which is launched here and would have been delivered in case I had put a resistor at this location itself, which was the earlier situation we just looked at. But right now it has to travel this distance. In order for the same kind of power transfer to happen to this particular transmission line has to have a specific property, actually two specific things. One is sort of obvious, that this transmission line should not dissipate any power. This, of course, is impossible at room temperature operations because these are all made out of the metals, but it can be made small enough. But more importantly, it should transmit this power, which is now going to propagate as a wave along this transmission line without any reflections. And that requires this transmission line to have a property Z0 also equal to 50 ohms. Okay, and this Z0 is what is called characteristic impedance. Okay, characteristic impedance. My handwriting is terrible, so just if you are not able to read something, just let me know. Okay.
Sorry, sir. Sir, then there is the effective resistance then 100 ohm, right, in the external circuit. So how that impedance having condition is satisfied?
That's a good question, but it's not 100 ohms. So if I look at the resistance, so this is why I use that word. Characteristic impedance is not the same as resistance or impedance, and we will look at that in more detail. But just to answer you the question, if I looked at this just from a low frequency point of view, even though that is, it is correct even for the low frequency picture, but it is not relevant. If I measure the resistance of this point, which is the center connection, and this point, that resistance will be 0 in the ideal case. Similarly, if I measure resistance between this point and this point, that resistance will be 0. So in the low frequency picture, this is just like you connected two wires between these two circuit points rather than connecting them directly to each other, right? Imagine building this on a breadboard. And they say this source is at one location on the breadboard and this resistor is at another location on the breadboard. And you just connected wires, right? And those wires will have maybe 1 milliohm resistance, much smaller than the 50 ohms. So the maximum power transfer still works. So the characteristic impedance actually has a very different meaning, and we will basically discuss that as the last topic for today. And that's what ensures it's actually got to do with the ratio of voltage and current at any point along this transmission line. So it's a property which is similar to things like refractive index of a material, or something you have come across, which is the characteristic impedance of free space. Does anyone remember that number? It's related to mu naught and epsilon naught. Impedance of vacuum. No? 377 ohms. Does that ring a bell? I can actually, again, never remember, but I think it's this. No, it's not this. Sorry, that's probably the velocity.
mu naught by epsilon or 2 over half.
Exactly. It's mu naught over epsilon. Yeah. Okay. And this is actually a nice way to segue into the topic of transmission lines. Of course, this is talking about free space, but does any of you remember the units? There are several ways of defining that, but a very common unit for mu naught and epsilon naught, do you know how they are defined? Anybody? We remember the values, right? Epsilon naught is 8.854 10 to the power minus 12 watt. One. Oh, okay. The units are, this is one way which is easy to simple unit, is actually henries per meter for mu naught and farads per meter for epsilon naught. So this is henries per meter and this is farads per meter. So henries and farads are, of course, units of inductance and capacitance. So these are inductances and capacitances per unit length. And that is what now in the context of free space is a little bit tricky to imagine in this language. But for a transmission line, it's exactly what this quantity is. And this determines how the voltage and current at any point along the transmission line will be. And it's this number which has to be 50 ohms in order for there to be no reflection as these points. So here again, there's a combination of lumped element description and wave description, that there are these points, you can always have points which are spatially localized, and you can of course define currents and voltages at those particular points. But then from this point to this point, this transmission line has some voltage and current which is varying with space and time, of course, because these are all oscillatory signals. But at the boundary conditions, at the ends, you can again define those numbers. And that's what I mean by sending this ratio at all of those points is equal to this particular value, 50 ohms. And if you ensure that, then the signal will propagate without any reflection at this point. So, and again, the reflections can only happen at these boundaries, because after this, the transmission line is basically a uniform thing. So whatever reflection has to happen here, or it will happen at the next point where again the signal comes out of the transmission line and goes into the load. So if for some reason the Z naught is not 50 ohms, it's something else, then you will have reflections at both of these locations. Or if for some reason the termination load is not 50 ohms, but it's something else, then you will have a reflection on the right side, but not on the left side, because here the 50 ohms and 50 ohms are matching. Okay. All right. So now I'm going to clear this. And I'll show you here an example of this measurement. So I have plotted this, and I'm going to define a measurement now. So remember, I have to go to electromagnetic. Linear port parameters. S, I choose the schematic. And since I have only one port, I can only define this one quantity here. And I'm going to plot, let me plot magnitude, and let me plot phase. So I can use this add button to add multiple measurements of the same type. So you can see it has come here. Now magnitude and phase are of course very different quantities. So it helps if I plot them on different axes. So I'm going to go here, go to options, and then under measurements, I can change the angle to the right axis. So that way these will be easier to read. And I'm going to check the frequency here again, project options. Let me make this from 1 to 10.1 megahertz. Okay. Now, before I run this, I want you to guess look at this circuit. I'm plotting S11, which means the ratio of the signal which is reflected to the ratio of the signal which is sent in. Okay, that's what S11 means, voltage ratio, and I'm going to plot the magnitude of that as a function of frequency. Now, I'm sure all of you have seen this parallel LC circuit. You know it's going to have a resonant frequency, which is 1 over square root of LC over 2 pi. And I think it'll be around 5 gigahertz. And this is only for the students taking this on credit. And I know there are some senior people who might be familiar with this idea. What will the magnitude as a function of frequency look like? Any ideas?
At the resonance, it will be highest and drop both side of it.
So you are saying that the magnitude is going to look something like this. Is that right, Shikhar?
Yeah. Right.
Can you motivate your answer?
So, we have done this pulse pendulum experiment. So we see at one particular driving frequency, we find it to be highest, and then at other frequency it just drops out. So using the same analogy, I just put it.
Very good. You are walking into a nice low frequency trap, which will help me to emphasize the differences between microwave measurements and conventional measurements. But you're right. The way you're thinking about it is right, but it is not applicable here. Now, you have, of course, I'm sure, I remember doing an LCR experiment in my undergraduate days. But what do you measure in those cases typically? You will measure the voltage across a component, or you will measure a current through a component as a function of frequency. And you're absolutely right that in such a case, you will see some kind of a peak or maybe a dip. Remember what S11 means, right? We will, of course, define these quantities in more precise ways earlier on. But S11 is a scattering parameter. It only talks about reflection of waves or transmission of waves. So remember that this thing is a 50 ohm source. So it has some ideal voltage source and the 50 ohm thing over here. And in this particular circuit, there is nothing between the port and this thing. So it may be a little bit difficult to imagine, but just consider that there is some transmission line here, right? Some finite transmission line, which is again 50 ohms characteristic impedance. And this launches a wave, and that wave goes like this. So, there's some wave here. It goes like this. It reaches this point. And this, of course, is not a 50 ohm resistor to ground. So it's going to reflect backwards. And it's going to reach the port again. And remember, the port also has this detector. Maybe the detector is somewhere over here, which is looking at this. And what it is really calculating is what was the amplitude of the wave it sent. So the voltage across these 2 points when it sent the signal, and the voltage across these 2 lines when it received the signal back. And it's plotting that ratio. Okay. So, I mean, this is a new concept to most of you, but I'm trying to see whether you can guess whether what you said that at some point you're going to get a peak. So what does it mean to get a peak or a dip? Remember that this
Okay, so
source,
it's a reflected wave, so we actually get the inverse of that curve. At one point we get the dip, and other two sides, it's the most reflection that will.
so you're saying it will look like this now, like a
Yeah,
dip.
so it's reflected, yes. So
But can you tell me why the reflection will be more or less?
okay, it's like boundary condition when we have done this wave thing. It depends on the boundary condition that it is
Well,
the impedance matching. I think
this is the boundary condition, right?
yeah.
Okay, let me ask a slightly different question. Let's say I did not have the capacitor in the circuit. So let me actually go ahead and delete this. What will be the magnitude of S11 as a function of frequency for this circuit? Anybody? All right, let's see this answer first. So I'm going to disable the angle for a moment. I'm going to only look at the magnitude. Let me solve. Remember, magnitude is plotted on the left axis. So look at the left axis. It's 1 at all frequencies. So another interesting tool you can do is you can right click and add a marker. So it tells you what's the value at a particular point exactly if you want to read it. So I can put a few more. So the first point is telling you the frequency. The second point is telling you the y-axis. So it's 1, 1, 1. It's exactly 1 at all frequencies. And let me clarify that it is not a resolution issue, that there is some feature which we have not been able to see because I did not sweep the frequency fine enough. This is exactly the answer. It's 1 everywhere. Now, let me ask you another slightly different question. I'm going to put the capacitor back. I'm going to delete the inductor. Now, can someone tell me what this curve will look like? No? It's also 1 at all frequencies. Confused? How many people are completely confused by this? And this is, by the way, correct. Raise your hand if you're really completely lost it. Like, I have no idea what the hell is going on. Okay. Oh, I still see many people who have not raised their hand. So maybe one of those can answer. Not again, not the senior people. I think some of you might already know this. Okay, I guess we will ask one of Aishi, can you explain what's happening here?
Sir, what I think is that these L and C these are like non-dissipative parts. And so we would have seen a dip if there was some dissipation across. So yeah, that's my thought, kind of.
Okay, that's right. You can all raise your hand, lower your hand. But now let me ask one of the first years. So Panya, I'm going to put back the inductor. Can you guess what magnitude as a function of frequency is going to look like now?
Since they were both 1, so they might be 1 and -1, so they become 0.
Tough luck. It's actually, remember, it's absolute value of the magnitude, right? So magnitude value is absolute. You can see this little absolute value here.
Yes.
But it doesn't, I mean, magnitudes are just positive by definition, but it's also 1, right? So this is, again, looks very strange and surprising that you are basically trying to measure a resonant circuit, but this quantity magnitude as a function of frequency is showing absolutely no information. Like, how do we know there is a resonant frequency, right? For this circuit, it's 1 over square root of LC over 2 pi. But this thing is showing absolutely nothing. So now I'm going to enable the phase. Okay, and let me disable the magnitude so that's clear. Now you see something, though this is not so obvious for those who are not familiar with this. Let me adjust the right-hand side axis a little bit so that I can explain my point a little better. Oh. Okay, so you see this quantity. Now we have to look at the right-hand axis. Remember, this is phases on the right. Let me add a few markers. Okay, so at low frequencies here, it's showing a value of plus 157 degrees. At high frequency here, very high frequency, it's showing a value of minus 130 degrees or so. So Panya, your idea about something becoming positive and negative, you can see it shows up here because the magnitude did not have a sign, but you are right about that, except that it doesn't cancel everywhere. Okay, and somewhere in the middle there is a value which is close to 0. So in fact, I'm going to zoom in here and I can drag this marker and make this value as close to 0 as possible. So there it is. Right. So the phase is 0 at this value of 5.03 gigahertz. Okay. From this, can someone tell me what the resonant frequency is?
5 gigahertz.
Yeah, maybe some of you have already computed this number on the back, but here's another a little microwave office thing for you to see here. I can do a calculation here. So I can do one. So let me define f res equal to 1 over square root of 1e minus 9. That's the inductance multiplied by 1e minus 12. That's the capacitance. And then the whole thing divided by 2 into pi. I don't know if pi has a, remember, so let's say 3.1415926. And in order to see the value, you have to do something like this. You first define it, and then you say f res colon. Okay, and then you just run. You have 5.033 into 10 to the power 9, which is exactly what we had here. Okay, so the reason, and of course the magnitude we already saw was constant. So as Aishi said, the reason there is no change in the magnitude is because this circuit is made of purely reactive components. Remember, this is an ideal situation. This is an inductor. This is a capacitor. It cannot absorb any energy. There's a caveat, which I'll come to that in just a minute. Hence, the entire signal is reflected. And at all frequencies, because at all frequencies, both capacitance and inductors are just have different reactances, but they're still imaginary reactances. So it has no information in the magnitude of the reflection. The information is all contained in the phase of the reflection. And it just so happens that the phase of the reflection goes to 0 exactly at the resonant frequency. This you can calculate once you know the formula for the reflection coefficient, which I'll mention in a second. And that's how you know the resonance. Now, there are other quantities you can plot which show dips and peaks. So one useful quantity is actually the real part of the mag. So remember, the magnitude is basically real plus I imaginary mod, right? Mod of that. If I now go here and I sorry, I'm going to duplicate this and I'm going to plot the real part. So now you see this brown curve here. This is the real part, and it has a peak exactly at the point where the phase goes to 0. Okay, so the real part has a peak in this. This is not the same type of peak which you were discussing before, but this is just to tell you that a real part of this has a peak. Let me duplicate again and show you the imaginary part. The imaginary part has a 0. I'm going to disable the angle for a moment because it's confusing here. Let me. So again, look at the left axis here, right? So you can see this real part is going from -1 all the way to +1, back to -1. An imaginary part is going to like towards 0 here. It goes through 0 at resonance, and again, sort of going back up towards 0. Right? And this is actually connected to what Panya was trying to say, even though there's no exact cancellation everywhere. What are the limiting values of this impedance at the various points? So we know that at resonance, the impedance of this circuit is actually how much? Ishita, do you know what is the impedance of a parallel LC circuit at resonance? No? Priyanka, do you know?
We can calculate it from doing.
Yeah, you can of course calculate it, but do you remember what's the impedance of a parallel circuit? It's infinite. Okay, for a series LC circuit, it's 0. So it's infinite at the resonant frequency. And remember, what are the values of the reactances? So XC is, I'm just not putting the imaginary part here. XC and XL look like this, like the imaginary part of the impedance of an inductor goes as omega L, and for capacitor goes as 1 over omega C. So if you go to very low frequency, so let's say omega going to 0, then XC goes to infinite and XL goes to 0. So what is the parallel combination of an infinite impedance and a 0 impedance? It's a 0 impedance. So at very low frequencies, it looks like a short circuit to ground. Similarly, at very high frequencies, so if omega goes to infinity, this goes to 0 and this goes to infinity. And again, infinity parallel with 0 is 0. And hence it goes to 0. And that is reflected in the imaginary part going to 0 and the real part going to -1 at both of these things, because these are both short circuits. And if you look at the boundary condition, you will see that for a short circuit boundary condition, the waves will invert. And I think Shikhar was trying to refer to that. So they will reflect with a sign -1. And again, you have seen these kind of things in quantum mechanics and other wave scattering things, that the sign inverse. But at resonance, the real part is 1 and the imaginary part is 0. So that's why there's no phase shift. It's 0 phase because it's entirely along the real axis. And it has also a phase of 0, and the reflection coefficient is always, magnitude is always 1. Okay. Now, to end this discussion, and we will of course study this LC oscillator in way more detail. We will try to understand what this curve is, what can you extract from this curve, why is the curve this particular shape, and in one assignment I'll ask you to derive the analytical expressions for these curves, because they're fairly straightforward. The caveat is this. The argument we made was that these are reactive components, hence they cannot absorb any energy. Oh, maybe just to finish that thought, let's go back here. I'm going to disable all of these, leave the magnitude on, but I want to show you what happens if you now introduce dissipation. So how do we do that? We just put a resistor. So I'm going to go into this lumped element, choose resistor, and again use the simplest resistor here, closed form, drag it, and put it in parallel here. I can choose any value, but just for fun, I'm going to make it 50 ohms. Okay. Aishi, can you guess now what the magnitude is going to look like?
There will be a dip at around the resonance frequency.
Right. So exactly at the resonant frequency, there is a dip, and look at the left axis, it's going to 0. Why is that? You can just use the idea we just discussed. At resonance, the LC part goes to infinite, like it's infinite imaginary impedance. It's in parallel with this thing. So infinite and this thing in parallel, the infinite basically doesn't count. All the stuff goes to the resistor. So now you're only left with a situation where, this is not there. This is not there. You just have 50 ohm source on a 50 ohm port, and this is impedance match. So you have maximum power transfer which means no reflection. And that's why this goes to 0. But exactly only at that particular frequency. At other frequencies, you have reflection because the load is a combination of some reactive part and some resistive part. Okay. And if this was not 50 ohms, and here I can introduce another concept of microwaves. So hide this, and we will stop after this, already getting a little late. Okay, so you see this little screwdriver kind of thing here. It says tune tool. This is what you can use to change the values of these components real time and see what happens. So I go and I click on this. So it becomes blue. And then right next to this, there is a little slider for tuning. Okay, so this now gives you this little window. And go back to the graph. And then I can try to change this. So I'm going to show you another, let me get rid of this. Yeah, one more useful thing is when something is drawn here and you want to compare it to other things you're changing, you can go to the graph menu and you can say freeze. So it sort of saves a lighter version of that image on the screen so that it always remains there. You can compare what happens. So now I can go here and using my cursor or my mouse, I can change. So I'm going to now reduce the impedance. Instead of 50 ohms, it is now getting lower and lower. And of course, it's non-zero in other places, but now even at the resonant frequency, which was around 5 gigahertz, it's non-zero, right? It's giving you a reflection coefficient of 0.3. Why is that? Because you can just go back to the same argument. The inductor, the parallel LC circuit is still not present effectively at resonance, but now it's a 50 ohm source driving a 25 ohm load. So you don't get maximum power transfer. So you have some reflection. And that's what you're seeing here. And if I go to the other side, so I go back to 50 and I increase it. Sorry, there is 50. Oh, sorry, this is 50. I changed the something else. It again comes back. So it can only be minimum at exactly 50 ohms and it comes down, goes up on other directions. Okay. So hope this is clear. Now to finish up with that caveat I was mentioning, let me get rid of this again. We said that because these elements cannot absorb energy or dissipate energy in the ideal sense, any real inductor or capacitor you make will always have some dissipative component. And we'll be looking at that later on how to model that. It's reflecting everything. But that somehow seems inconsistent with a picture that if I really think of this as some, this box as a voltage source with a resistor, and now this is driving my LC circuit, we know that at resonance, there is going to be some energy in the inductor and in the capacitor. There is going to be some voltage and current which is flowing through. So how is it that if this cannot absorb any energy, then how is there energy in this circuit in the first place? Because remember, if you think from time t equal to 0, when you maybe turned on the signal, initially there was nothing, there was no currents or voltages here, but all the signals were reflected and yet no energy is here. It seems to be inconsistent with this idea, okay? And this is because when we talk about scattering parameters, we are always talking about a steady state scenario, okay? You have all studied differential equations and especially second order differential equations which represent oscillators and maybe even driven oscillators. You must have done that. They have two solutions, right? There is this transient solution and then there is the steady state solution. When you write down solutions for oscillators, you always write down a steady state solution and you plug it in and you see it. That is after the steady state is reached. And that is where the entire scattering parameter picture, which is always in frequency domain, is always in steady state. So obviously, if I look at the reflected signal as a function of time, so what do I mean by that? I have this circuit here. Initially, there is no voltage, charge, current, nothing on this circuit, and the voltage source is off. And then I turn the signal on at time t equal to 0. And I look at how the reflected signal is as a function of time. It will not be 0. Or sorry, it will not be 1. Initially, when the energy is getting built up, there will be some reflection and some absorption and the reflection will not be exactly 1. It's only after it has reached a steady state, which will correspond to whatever the voltage source value is and the 50 ohm resistor and the value of L and C's. In the steady state, what you will see is that the amount of signal you are sending in is the same as the amount of signal that is coming out, and the amount of signal which is present, or the energy which is present in the LC circuit, is constant. So that's what is steady state. So those voltages and currents won't be changing. But this is the caveat you have to remember, that scattering parameters are always in the steady state binary. You're not looking at the transient part. So, but the energy has to build up, and one can, of course, solve the differential equation of, this is a very simple thing, and see these transients. And then also notice that in the steady state, you do have the situation that the energy which is reflected back is equal to the energy that is sent in. And you know that that has to be true, right? Because steady state means that the energy of this oscillator has reached its steady value. It cannot go up. And if it cannot go up, whereas your source is still on, and it's still sending energy in this direction from left to right, then that means all that energy extra it is sending after the system has reached steady state has to come back. So this is sort of maybe the physics way of thinking about like what is really happening when you reach steady state. Okay, so let's stop here. I guess I didn't get to the transmission line, but that is a fresh topic, so we can do that next time to really look at what a transmission line is, what is the meaning of these waves, what is the wave equation for that, and where does the characteristic impedance come from, how do we connect it, concepts we already know from electromagnetics, waves, and wave theory. Okay, great. So maybe I can take a couple of questions, if there are any, about this part.
I have a question regarding the measurement of reflected, how it is measured. I mean the delivered power, we are measuring the voltage and current across the external circuit, and the reflected power, how do we measure it?
So it's the exact technical detail is something we will discuss later on in the class, but basically there are circuits in these instruments. So this particular instrument is called a vector network analyzer. If you're actually talking about in real life, in practice, how it is done, it has a mechanism. So there is basically a black box here, which I'm calling it a black box because I'm not going to tell you what's in there right now. And then this is going to your circuit. So let's say this is your LC circuit you have measuring. It has a mechanism where the signal which is coming in this direction is diverted to a different location. And then here you have a sensor, which then measures the voltage at that point. And this comes from the property of this particular device, and we will be studying such devices later on in the course. It allows you to separate the waves going in two different directions. So in one direction it will go, and for the forward going wave, because it is generating the signal, it knows what that magnitude is. For the reflected signal, it is able to divert it into a different direction, and there you have put a different sensor which measures it. So that's how actually you are able to measure the reflected wave separate from the incident wave. To complete this answer, if you are talking about how we will do it in calculation, there you can just basically write down how you do it for a quantum mechanical, say, a scattering problem. You write down the wave equations, you write down here remember that at any point in space, the voltage is going to be the sum of the right going and left going voltage waves, right? So we will see these kind of examples as we go on. So there you can, by having enough equations and enough boundary conditions, you can separate these quantities out. And as I said that I will ask you to calculate these responses of the real, imaginary, and all of those quantities for the simple case. So you will see how these calculations are done at that time. Is that clear?
Yeah, it is clear.
Anybody else? Okay, great. All right, so I will send an email about when the next lecture will be. Again, sometime early next week remotely, because I'm still away for the whole of next week. But we will do it online like this. Okay, all right. Thank you, and I will see you next time.